What's up, guys? This is going to be a pretty quick lesson, just a couple problems here, and then a decent list of vocabulary words. So go ahead and pause and write all these down. First word here is a dependent variable. It says it changes in response to another variable called an independent variable. It depends on something. For instance, you depend on your parents to make sure that you have food. That makes you a dependent of theirs. The same thing could be said for a dependent variable. It depends on something else doing something. The value of independent variables are called inputs in functions, and dependent values are called outputs. Okay, so an independent variable is just some number that exists. A lot of times these are considered x values. Outputs are the values that we get from doing something to the input. And oftentimes you'll see those be y values. A function is a relationship that pairs each input value with exactly one output value. And we'll talk more in detail about what exactly that looks like a little bit later in another lesson. This one, a linear function, is a function whose graph is a non-vertical line or part of a non-vertical line. So make sure you have those copied down. And we'll move right along. But before, here's just a moment of truth that everybody that's watching this video in all of America can relate to. When I do it, it's fun. When you do it, it's the most annoying thing on the face of the earth. Absolute truth right there. All right, so patterns in linear functions says representing a geometric relationship. In the diagram below, what is the relationship between the number of rectangles and the perimeter of the figure they form? Represent this relationship using a table, words, an equation, and a graph. So notice here that we are being asked for 4 different things. All right, so let's start with the table. First thing that we can think about is we'd have the number of rectangles, which this would be an input, and then we could have the perimeter, and that would be considered an output. And it doesn't have to be a real fancy table. In fact, a T-chart's fine for me. All right, so when I have one rectangle, the perimeter is going to be 1 plus 1 is 2, plus 6 is 14. Then I go and I do 2, so that's 1, 2, plus that's 8, 9, 10, plus that is 16. And then for 3 rectangles, I have 1, 2, 4, and you just count, and you could probably kind of see that there's going to be a pattern here that's developing. So there's my table, and that's good enough. With words, all right, how would you say this in words? Well, I'm not going to write this out just because I want to save the space on my slide, but if you were writing this out in words, you would say something along the lines of the number of rectangles times 2, okay, because I have 1 here and 1 here, 1 here and 1 here, 1 here and 1 here for 2 rectangles. So for each rectangle you add, you are adding 2 to the perimeter for this top little part and this bottom little part. And then you'd say plus 6 for the 2 sides, or plus 12. So the number of rectangles times 2 plus 12 is the best way to say that in words. And if we translate that to an equation, we would have y is going to be our output, is going to equal the number of rectangles times 2. So we'll say the number of rectangles is x. And then I add the 6 and the 6, which is the same thing as adding 12. All right, so there's my equation, 2x plus 12. And then the last thing is to represent it as a graph. And your graph may look a little bit different, but I would think of it like this. I would have 1 rectangle, 2, 3, and 4. Now these values go up there pretty quick, so I'm going to make this go up by 5s. So 5, 10, 15, 20. All right, so when it's 1, it's 14, so I'll put a dot right there. When it's 2, it's 16, so that gives me a dot. 3 is 18, just a little bit below the 20. If you're using graph paper, obviously this would look a little bit nicer and neater. I encourage you to do that. But that's how you would represent that graphically. Yeah, so there's my 4 things. Hopefully you followed along with that. If you have questions, make sure that you are bringing those up in class. Let's take a look at another one. It says, the table shows the relationship between the number of photos X you take and the amount of memory Y in megabytes left on your camera's memory chip. Is the relationship a linear function? Describe the relationship using words, an equation, and a graph. So the first thing to pay attention to is, first of all, how do these values change? So as I go from here to here, I am increasing by 1 each time. If this has a common increase, the next thing I want to do is look for what is common here. Well, I see I go from 512 to 509 to 506 to 503. It looks like 3 is being subtracted every single time. And any time you have the same value being added repetitively or subtracted repetitively, that creates a linear function. So we know that this is going to be a linear function. You probably want to make note of that somewhere in your notes. So let's go ahead and make these words, an equation, and a graph. So again, I'm not going to write out the words. You need to write out the words, but I'm not going to, just for the sake of saving room on my slide here. What you could say is something along the lines of, as the number of photos increase, for each photo that you increase by 1, the memory is 3 less. That's one way you could say it in words. Another way you could say it in words is starting here with this initial value of 512. That's how much memory is on the card before any photos are taken. And you'd say 512 megabytes minus the number of photos times -3, or something like that, or minus the number of photos times 3, not -3. I misspoke there. That's another way you could say it. All right, so then we would want to describe that relationship using an equation. Well, we'd say this is my X value, this is my Y, so the Y value is going to equal, just like we were saying in words, 512 minus the number of photos times 3. So we'd say minus 3x. 512 minus 3 times whatever this number is. And you can check this out. This works every time. Also, whatever this number is, if it's the same value going down, that is always going to be the value that you are multiplying your x by. All right, so that's a handy little trick to keep in your back pocket. And then how do we represent this as a graph? Well, let's start with 0, 1, 2, 3. Now these numbers are way up there, so I'm going to put a little break in this. You guys have seen that before, hopefully. And I will make this, let's see, we'll say that this value right here is 455, 500, 505, 510. Whoops. 515. All right, so when it's 0, it's right here at 512, and then we're at 509, and then 2 is 506. I didn't space my stuff out very well here. You should probably take more care to do that better. But you could see how if I would have done this evenly, it would create a line. So you would write that this is a linear function. All right, so that's what we're going to be working on in class. I believe that's it for this slideshow. Yep, so I will see you then. Hopefully you took good notes. Have a good evening.